I made a string library in C from scratch. It has one struct, 10 functions, and 2 macros of a public API. In this video, I'm gonna tell you why and how. Why is actually pretty simple. Every time I have some project in mind that I want to make a video about and it involves strings, I feel dread because I just don't want to deal with C strings, especially if it involves something like splitting strings or prefixing strings or trimming strings and stuff like that. I just don't want to deal with all these like things from string.h, and it just gets me demotivated. And recently I just been thinking about another cool video and it needed strings, and I just said enough is enough. If I'm gonna use strings in C, I just have to get some normal human strings that hold size information. And I also have a little test file here that just goes through very basic scenarios that if I run it, you can see what we can do with our strings. So first we can just simply count them, the amount of characters, then we can split string by separator and it correctly handles empty strings, it correctly handles separator of one character, in this case a comma, you can see it preserves all the white spaces, correctly shows how many splits it has. It can work with separators with more than 2 characters, so in this case double semicolon, and it correctly handles UTF-8, which kinda comes for free but still testing it. Also, it correctly handles situations where separator is leading and trailing as kek in this case. So here it works the same as string.split works in Python, so it preserves leading and trailing separator. Also, it handles buffer limit, so I will showcase how split works, but if, for example, you provided a buffer of insufficient length, it will correctly handle that as well, and it can also trim strings by white spaces, and it also can convert string to C string to be compatible with system APIs. This is literally all I need from C string library, at least for now. And so here is how I did it. And also an alternative way that I considered but decided to not go with. So C doesn't really have a string type. What it has is character star, which is a pointer to the first character in supposed string. The way it's represented is by just a sequence of characters like A, B, C, D, whatever. And at the end of this string, you have null, like literal 0. And the way C works is that it uses this literal 0 as a way to terminate string. So it's called null terminator. And it is very annoying because every time you need to know the length of the string, you need to call a function strlen that will count this string one by one character until it encounters this null terminator. And there are a lot of food guns associated with it. So a lot of modern programming languages, they do something different. They still use this character star because you can't really escape it, and they pack it into a struct. So they create a struct that has this character star, but additionally they have another field that is called count, which is an integer. This way, by adding a level of indirection, you can pass this struct as a single unit and create a bunch of functions that operate on this struct. One of the biggest advantages of this approach is that now most common operations with a string, they don't require additional allocation. So if you want to split the string like in half, like that, instead of allocating a separate buffer and putting AB there with a null terminator, what you can do is you just literally create another struct, and this second struct will have its data pointer pointed at C. So it uses the same exact backend memory, it just points at a different part of it, and its count will just be 2. And the first struct will point to AB, also will have count 2. This way, you don't really need a null terminator at the end. You can still have it for certain strings. In this case, you can almost pass a character star in a system API as is, because all of them require null terminators. But if you just work with string at your high level in the library, you don't need null terminators anymore, which is very convenient This reduces allocations by a lot, and it also means that you can freely share the struct across many different functions, and you don't really have to keep track of the pointer. So this is great. I think that's a great approach, and this is what I went with. But there is an alternative approach that I considered but dismissed. Let's talk about it as well. So the second approach also starts with character star, A, B, C, D. But the way it adds a count, and let's remember that the whole ordeal is to attach a count to the string somehow, is it literally puts the count here at the start of the array. So your character star does not really start with ABCD. It literally starts with the literal 4, then it will have ABCD, and then it will have null terminator, just like that, in a single allocation. And then when you ask for the character star out of it to maybe pass it to some libc library functions or to some system call, all the functions that deal with a string, they just return you a pointer that points to A. So whatever API you work with, it doesn't know about 4. But then if you provide this same string to any of your library functions, it will know that the first character is always prepended by some kind of a header. Usually it's just a count, but sometimes they can pack more information there. For example, they can keep the allocated string capacity, right? So in case you need to merge two strings together, it can check whether one of the strings has additional space, and so it maybe doesn't need to allocate more. There are multiple optimizations you can do. If we compare these two approaches, both of them have advantages and disadvantages. So for example, as I said, this approach, the first one that I went with, it has a level of indirection, which means that every time you need to access underlying character star, you need to go through like a pointer dereference if you pass a string by pointer or something like that. And the, I guess, biggest disadvantage, you can call it, is that you need to allocate the character star and a holding structs separately. And in theory, it is more complicated because you need to keep track of the struct memory and you need to keep track of the character star memory. And then, for example, if you need to pack the strings into a single array, you would usually need to fetch all of the character star chunks to put them in the same array and then pass somewhere, because usually you would have array of strings and each individual string, you know, will point to different memory location for its character stars. So you can argue worse cache locality. But modern libraries, they usually provide a separate facility for this that is called like a string builder, where you can just put individual string chunks. So this issue is circumvented. But here in this case, main advantage, you can kind of see it, is that first, it's super compatible with all libc functions and syscalls. So you can almost use this as is. All you need to do is to point slightly further ahead of the allocated buffer. Additionally, you only need one allocation to allocate the whole string. So you don't need to allocate a separate struct. You don't need to keep track of this struct. All you need to do is this. But it comes with a bunch of disadvantages. So first of which, you always need to guarantee a null terminator at the end, which means what? If you want to split the string, you need to do another allocation to put this chunk into it, because you need to do what? You need to postfix it with another null terminator. This is the first main disadvantage, and I guess almost all functions that operate on the string need an additional allocation because they also need to hold this number, right? Because here the number will be 2, and then the remainder string here, it will also need a number 2. I guess you can technically put it in place of the old string and then pass it like that. You can optimize some of it, but you still need more allocations. And another even bigger downside is that if you need to pass the same string into multiple functions and then you need to modify it. So imagine you have a bunch of places where you passed this particular string, and then these places, they hold the strings, and then you need to modify it. You need to go through each individual pointer to the string and update it. And this is like a big pain. So what proponents of such method, and by the way, this style of doing counted strings is called Pascal style because it was originally implemented in Pascal, I guess. But anyway, the way proponents of such approach recommend you to deal with this shared pointer issue is they recommend you to wrap it in a struct that you do reference counting on, which is in hindsight is not that different from the original approach, right? So why bother? But if for some reason you like this approach, there is actually an existing library that is made by Antares, who is creator of Redis. It's called SDS, and here he kind of explains how it works exactly the same way as I described. I guess diagram is nice, right? And now let's talk about implementation of mine. Okay, so this is an STB style library, which means it is a single header library inspired by very famous programmer Sean Barrett, who worked at Looking Glass and made games such as Thief and System Shock. Yeah, and so the way you make these libraries is that first you define declarations for all your API, and then you check if def implementation. And if a user provided this define, then you give them implementation. Otherwise, you let them to implement defines themselves. You also have this string def prefix that a user can declare either as static or as extern if they want to compile this library as a separate compilation unit. And so the way it's used is like this. So you declare string def as static, then you define string implementation, and then you include the library. And this will let you build this whole program as a single compilation unit. So this is kind of the flexibility of STB libraries. It starts with a struct. I use count as 64-bit integer because it doesn't matter if I put anything smaller here, the struct will still be 16 bytes because the rest will be taken by the padding. Because pointers on my 64-bit machine are also 8 bytes long. And you can say that I should have used unsigned 64-bit integer here, but I stole this idea from Jai programming language where counts are also signed, and they are signed in case you underflow the count. So then it's negative and clearly wrong. So I kind of went with the same vibe here. After that, I have a static define for all white spaces. So I have 6 white spaces here. And then I have my first define, which is string spread. And it literally expands into count that is casted to int and data. And I'm using it to printf my string. So regularly in C, in order to print string, you provide %s to printf and you give it a null terminated pointer to character star. But in my case, sometimes, or I would say most of the time, strings are not null terminated. In this case, you need to provide this formatter, which is %.s. And that star means that you need to provide a count. And this is where I'm using this macro, string spread. So it spread my lit empty that I define here and literally pastes count and then data. And then here are public functions. So first of them is string make. It's very simple. You just provide a char star and count and just packs it into a struct and returns it to you by value. Second of them is string from C string. You just provide a regular C string that is null terminated, and I call strlen here to get the count. And you might notice that I am not using string.h here. This is a conscious decision. I needed to decide whether I want to implement my string library on top of string.h or completely independent, and I went with the independent way, even though it's, it's clearly suboptimal, right, compared to what, for example, glibc uses. But yeah, it's very simple. It literally just iterates over the character star until it encounters null terminator, and then it returns resulting count. Then I have equality operator, you might say so string eq that returns a boolean, and it is very simple. It literally checks the counts first, then it checks if strings are pointing to literally the same character star. So if they share exactly the same pointer, then I obviously don't need to iterate over them. After that, I have a simple loop that just just goes through each and individual character of both of them and it compares them. And so if any of it doesn't match, it returns false. And again, I intentionally do not use memcmp here because I don't want to rely on string.h. And one of the reasons why is I was thinking that at some point I want to explore SIMD in C, and simdefine memcmp here in my own library would be a nice exercise. So maybe at some point I will make a video about it. No promises though, but let me know if you're interested in something like this. After that, next obvious one is whether string starts with something. And this one I actually added while working on split. So let's first talk about split. You might say, over-engineered it a little bit. The way user uses the split function is by providing an input string, a separator that is also a string, and then an output array that will get filled. And this array is bounded by some amount. So the caller needs to provide how many strings can fit into that array of strings. And it also might optionally provide a consume pointer that will get filled by another number. So let's go to the definition. Here it is. You can see it's rather big compared to everything else. First of all, it checks if any of these things is empty. So if separator is empty, if outbound array is empty, and if the input strings is empty as well. In this case, if output array exists, if it's not a null pointer, it will just put input string there. You know, like in case somebody forgets to provide this out count to the function, I don't want them to later, or I say them, but it's literally myself. Nobody else will ever use this library. I just don't want to blow myself up if I accidentally forget to provide this. Because then I will just look at the output string. I will see that it literally contains the input and it will signal that I forgot something. After that, after all the error conditions are checked, I start iterating over the input string. And as long as I still have something left in string and I still have space in the output array, that you can see that I initialize the first chunk by the input string, but with count set to 0. And I iterate over the string and check at each point, you can see here, if the string is equals to separator, or not equals, starts with. And here I was writing this function and I was like, okay, I need something that checks prefix. And the design of this function, it kind of motivated to create another function that is called start with. And so the way it is implemented is actually very simple. It just checks couple possible error conditions and then it just literally checks for equality. So it sets source count to prefix count, and then it checks whether they themselves are equal. Notice how I can freely modify input parameters like this because I pass them by value. All of my functions that do not intend to modify the string, all of them pass strings by value. So I can freely modify local copies of them without affecting the caller. I check the System5 ABI, and actually strings of this size, 16 bytes, at least on Linux, they are passed by registers. On Windows is a separate story. On Windows, they are passed by implicit reference, so the caller provides a space. But still, it literally doesn't matter. But this is a very nice sort of convenience that I don't need to be worried about modifying the caller accidentally. I just can modify it here. Just literally set a count, and then the data pointer that string is connected to will be bound by this count. So I can implement string start with in terms of my string ik, and then I can use string starts with in my split functions. And doing it like that, when you design your library in a way that more complicated functions are implemented in terms of less complex functions, it collapses code paths. It makes testing so much easier. So for example, just by testing all possible combinations of splitting logic, I indirectly test equality and I indirectly test prefix. It's very convenient, right? But anyway, going back to the split logic. So I check if my string string starts with the prefix, and if not, then I subtract the count from my input string. So what I'm doing here is that I bump the data pointer, so now it points to the second character, and I subtract the count so that the overall string is now shorter. So the way to illustrate it here, so if I have A, B, C, D, E, the way I do it is I bump the data pointer here, so now the receiver does not see this A, but since the string was 1, 2, 3, 4, 5 characters, now I need to subtract count, so it is just 4. And then I will bump the point here and subtract 4. It will become 3, and so on and so forth. And also I increase count of the output string, because as you can see, I put the initial data on the output. So the outbound array always starts with the input string. It just takes as many characters as needed before it encounters the separator. And also I bump the consumed. So let's hold on to this for now. I will explain this later. And here's the happy path. The way happy path works is that it decrements the out count because, okay, we found a separator, we finalized the first chunk, which means that the out count will need to be decremented to tell that, okay, we occupy a spot, so there are less spots left. After which, if there is still a spot that we can put our string into, then we do this. So first of all, we do this exact operation, but instead of doing it just by one character, we do it by the size of a separator. Then we advance the output array and we point it to the string data after the separator. And so I guess it's going to be easy to demonstrate with something like Python. So let's do this. And so in Python, if you have A, B, C, D, and you call split by a comma, let's actually do it like AA, BB, CC, DD, right? First it gets A and checks and it doesn't find anything, then it checks another A and it doesn't find anything, then it goes for the comma, then it bumps the array to the next pointer, it advances the input string by a separator, and then it points the second spot in the array to this part of the string. And so this way you can see that the output array, it does not include the separator itself because we kind of skip over it. But in my implementation, all of these chunks, they literally point to this memory. Yeah, hopefully it makes sense. And so I also bump the result that I define here, which will be then returned here. Yes, and so at the end I return this result. So this result holds a number of chunks that this function produced, and it can be up to out count. And this is where we get to the consumed part. I hope you're still following. So I am bumping this consumed pointer by the amount of characters I checked in the input string. And so why I need this? If for some reason a caller provided an output array that is smaller than the amount of chunks, then I can return the result of how many strings I was able to fit into the array. And also I will fill up the consumed so that a caller can potentially restart the string split with resized array, and they can also point initial input string to this index, you see? So if in our Python case, for example, if output array only had enough data for a ABB, then the consumed pointer will point to C. So the caller can say string.data equals consumed, and that's it. And then they need to subtract count by consumed as well. And so they can restart the split if they want to fill the rest of them. And if we go back to our testing, I have a case for it. Let me rerun it. And so the case is called buffer limit. So I provide input string ABCDE and I only give it 2 possible spots, and the result is 2, and you can check that 0 and 1 contain A and B, and then you would need to call this again with CDE. This is it. You might say that this is kind of over-engineered, but this is how I like it, and I could have made it much simpler if, for example, I would completely remove this part. If I completely remove this part and you just give it a pointer to the struct, and then the caller would need to control how much left and keep restarting the split until everything is consumed. I want to keep this loop here instead of putting it on the caller. So I think this extra complexity is worth it. And besides that, it's like what? It's like 40 lines of code. Come on. So split is the most complicated one. Next one is string trim left and string trim right. So you just provide a string and it trims for now white space characters, because I will definitely need to trim white spaces, and if I need to trim something else, I can just expand this function. And so the way it works, it just runs a double loop, so loop over the string, and it also loops over all the string white spaces, so over this little string that contains all white space characters. And it just checks if initial string contains a white space character, it advances the index, and at the end it just subtracts the count by as much white spaces we found, and also bumps the data pointer. So you can see in this family of string libraries, you do this operation a lot: bump the data pointer and subtract the count. And string trim from right does exactly the same thing, but it iterates backwards. And again, I could have included string.h and use isSpace function from libc, but I decided to do everything on my own, first as an exercise, and second as a potential for further exploration. And actually, let's stop here a little bit, because I actually looked at how libc implement isSpace. So here it is. So here is how musl implements isSpace. Super easy, right? So it checks if character is white space, and then it does a little trick where it subtracts tab character number from C and checks if it's less than 5. I found this super cute. It's a very nice optimization that keeps code very simple. And why it works? So it works because in an ASCII table here, if we take all of these, you have /t/n/v/f/r. They are all sequential. I think it's like 9, 10, 11, 12, 13, something like that. That's why you can use a math for these ones. And then space is kind of separate. It's like 32. And so musl does this, so it has less if conditions. But if we look at glibc implementation of isSpace, are you ready? So this is libc C-type header. isSpace is just one of them here. So you can already see kind of the shape of this file. It looks very confusing. Here is an actual alias for isSpace function, and it uses an X macro that I also had a video about, and it X macros it to some kind of capital I space, which is actually an enum. And then libc uses these enums to do some crazy beat math, and this beat math operates on a huge tables like here. So here, this is C-type.c, and if you scroll it, it looks very scary. And here libc holds a pre-computed tables of characters of different family, and space one is actually pretty simple. So here, this is a very small table of spaces. I haven't really researched it deeply, but here, just so you know, the way glibc checks if something is space is not by if-elsing through a predefined set of characters. It uses a huge table that it does a beat math on to support all possible cases under the sun, because of course glibc does it. And so the last couple remaining bits about my library is I have string to cstring, so you can pass a string from the library, and the buffer for the output characters that needs to be this length +1 for the null terminator, and I literally just copy characters one by one and add 0 at the end. Again, no mem copy here, I'm using it the old-fashioned way. And the last thing about my library is this macro that is called string.lit. So this is for computing compile time strings. So it calls string make with the character star that you pass here, and it computes its length at compile time by using sizeof operator -1, because at compile time sizeof contains null terminator, includes it, unlike calling strlen at runtime. And so you can see me using this string.lit in tests. This is how it looks like. String.lit hello. A nice thing about it is that getting a string from constants always has null terminator at the end. So I can spread it without worrying about converting to C string first. And so if I keep track of what's literal and what's not, I can kind of cheat like that a little bit. And so, yes, this is my entire string library. It's what, 200 lines of code. There's a lot of white spaces here, but yeah, it's about maybe 200 lines of code. And actually, when I just started my career, people used to scare me like, In the old times, before open source, every programmer needed to build their own string library. And I was thinking, damn, it must be so hard, you know. And no, in very, very basic sense, string library is very simple. This literally took me 2 sessions. So first session is I did some research for the options on how to implement them. And second session, I just literally sat here and I think in 3 hours, I had this ready with all the tests. And yes, I know it's not super fast because it doesn't use like crazy glibc optimizations. And also you might say it doesn't really support Unicode. You can't iterate over the string by Unicode graphemes. And if you want to do like to uppercase to lowercase, it won't really support Unicode. Then it doesn't have any allocated stuff. Like for example, it can't join anything. I would have to implement my own string builder, which I will probably do. But now I have a basis for my next videos that might involve strings, and I won't be demotivated by them anymore. And if while preparing for the video I realize I need some new functionality, I will just add it here. How about that? So that's it. Hope you enjoyed a little tour. Hope you understand my motivation. Feel free to comment, maybe, I don't know, roast my code, because every time I show some C code, people roast me for whatever reason. And I will see you in the next video. Thank you for watching. Bye.